Simple harmonic motion, which is used to describe such natural phenomena as the movement of a spring with a load applied, is modeled using trigonometric functions. In order to solve such models, the derivatives of trig functions are needed. Hi, my name is Jason Rosenberry, and today we'll be examining just that. Let's look at some formulas. Derivative of sine. The derivative of sine is the cosine. Derivative of cosine. The derivative of the cosine is negative of the sine. Let's try some examples. Find dy dx when, number 1, y is equal to 1 over x plus 5 sine x. Number 2, y equals 1 plus x minus cosine x. Number 1, y equals 1 over x plus 5 sine x. So let's differentiate each term. So therefore y prime would equal the derivative of 1 over x would be negative 1 over x squared plus the derivative of 5 sine x would be 5 cosine x. So y prime equals negative 1 over x squared plus 5 cosine x. Number 2, we have y equals 1 plus x minus cosine x. Therefore, y prime, differentiating each term, derivative of 1 is 0. The derivative of positive x is 1 minus the derivative of cosine, which is negative sine. Minus negatives make a positive, so y prime is 1 plus sine x. We use sine and cosine to model the motion of a weight bobbing up and down on a spring. Let's see how. A weight hanging from a spring is stretched 5 units beyond its rest position, which implies s equals 0, and released at time t equals 0 to bob up and down. Its position at any later time t is found by s equals 5 times cosine t. What are its velocity and acceleration at time t? Recall that velocity, v, is the derivative of s. So the derivative of s, the derivative of 5 cosine t, would be negative 5 sine t. Recall that acceleration, a, is the derivative of velocity. So the derivative of negative 5 sine t would be negative 5 cosine t. So the velocity at time t, negative 5 sine t. The acceleration at time t, negative 5 cosine t. Another application of the derivatives of sine and cosine is something called the jerk, which is defined as a sudden or abrupt change in acceleration. Let's take a look at its definition. Jerk. Jerk is the derivative of acceleration. If a body's position at time t is s of t, the body's jerk at time t is given by the following. J of t is the derivative of a with respect to time. It could also be found by taking the third derivative of the position function with respect to time. Studies have shown that motion sickness comes from acceleration whose changes in magnitude or direction take us by surprise. The jerk is a measure of the change in acceleration. Let's try an example. A. Find the jerk caused by the constant acceleration of gravity. G equals negative 32 feet per second squared. Part B, find the jerk of the simple harmonic motion of the previous example, s equals 5 cosine t. Part A, find the jerk caused by the constant acceleration of gravity, where that acceleration of gravity, g, is equal to negative 32 feet per second squared. So we just learned that jerk, J, is equal to the derivative of acceleration, which we could write it as dA dt with respect to time. And we're told again that acceleration with this problem is the acceleration of gravity, which is negative 32 feet per second squared. So we want the derivative with respect to time of negative 32. And we know that the derivative of a constant is equal to 0. So the jerk associated with the constant force of gravity is nothing at all, which is why if you are not moving, you don't feel any motion sickness, because the constant gravity pulling on you does not have any jerk associated with it. Part B, find the jerk of the simple harmonic motion of the previous example, s equals 5 cosine t. Well, in that example, we found that acceleration, a of t, was equal to negative 5 cosine t. So now we know that jerk is the derivative of acceleration. So jerk, j of t, which is equal to a prime of t, or the derivative of a, which would be what? Negative 5 times, the derivative of cosine is negative sine, so negative negative make positive 5 sine t. So the jerk function, j of t, would equal 5 sine t. Derivatives of tangent and cotangent. The derivative of tangent x is secant squared x. The derivative of cotangent x is negative cosecant squared x. Derivatives of secant and cosecant functions. The derivative of secant x is secant x tangent x, and the derivative of cosecant x is negative cosecant x cotangent x. Let's try these out. Find dy dx for y equals cotangent x over 1 plus cotangent x. So using the quotient rule, y prime would equal denominator 1 plus cotangent x times derivative of the numerator, which we now know is negative cosecant squared x, minus numerator cotangent x times derivative of the denominator, derivative of 1 is 0, and derivative of cotangent x is negative cosecant squared x, all over the denominator squared, or quantity 1 plus cotangent x squared. Now take a look at our numerator. We can factor out a negative cosecant squared x. So factoring out negative cosecant squared x, we are left with 1 plus cotangent x minus cotangent x, all over denominator squared, or 1 plus cotangent x squared. And as you can see, here we have a cotangent x minus cotangent x, which makes 0. So we're left with negative cosecant squared x over the quantity 1 plus cotangent x, that quantity squared. Show that the graphs of y equals secant x and y equals cosine x have horizontal tangents at x equals 0. For the graphs to have horizontal tangents means the slope is 0. So the derivative must equal 0 when x equals 0. So let's do y equals secant x first. If y is equal to secant x, then y prime, the derivative of secant, is secant x tangent x. And when we evaluate y prime at x equals 0, we get secant 0 times tangent 0, and secant 0 is 1 times tangent of 0, which is 0, and we get 0. So we can see that the derivative is equal to 0 at x equals 0. Using the same logic, we have y equals cosine x. Therefore, y prime would be negative sine x, and now we'll evaluate y prime at x equals 0. So we get negative sine 0. Sine of 0 is 0. So our derivative again is equal to 0 at x equals 0, showing that they both have horizontal tangents at x equals 0. Let's try one more example. Find the second derivative of y if y is equal to secant x. Let's start with the first derivative. If y is equal to secant x, then y prime, the derivative of secant x, is secant x tangent x. Now to find the second derivative, we'll differentiate the first derivative. And here we need to use the product rule. So the second derivative would be first function secant x times the derivative of the tangent function, and the derivative of tangent is secant squared x plus the second function tan x times the derivative of the first function, and the derivative of secant is secant x tan x. Now we simplify. Secant x times secant squared is secant cubed x, and then over here it seems that we have two factors of tangent, so tangent squared x times secant x. So the second derivative is secant cubed x plus tangent squared x times secant x. Now it's time for you to try a problem. Find the second derivative of y if y is equal to theta times cosine theta. Pause the video while you work on this problem. When you are finished, restart the video and check your solution. Let's start with the first derivative. So y prime would equal first function theta times the derivative of the second. Derivative of cosine is negative sine theta plus second function cosine theta times the derivative of theta, which is just 1. So the first derivative would be negative theta times sine theta plus cosine theta. Now it's time for the second derivative. Second derivative, again differentiating each term, we need to use the product rule with the first term. So again, that's first negative theta times derivative of the second, the derivative of sine is cosine, plus second function sine theta times derivative of the first, derivative of negative theta is negative 1, plus the derivative of cosine theta, which is negative sine theta. It's time to simplify. So we have y double prime is equal to negative theta cosine theta minus sine theta minus sine theta. So one more simplification. Our second derivative is equal to negative theta cosine theta minus 2 sine theta. In this lesson, we explored the derivatives of the 6 trig functions. Be sure to work the exercises that your teacher assigns, and we'll see you next time.